Okay, the tape kind of got cut off there, so I just want to make sure that we know that there are bonds being broken and bonds being formed in the process of dissolution, or basically dissolving is what we're talking about. So this diagram on the next page summarizes that it took a heck of a lot of energy to be invested to break up the sodium and chloride, and then they get surrounded by these water molecules, forming an ion dipole interactions. And remember, these water molecules had to kind of break themselves away from another water molecule because of that polarity. Water is very cohesive and it likes itself. It sticks together. So they got distracted by the ions and had to essentially break those hydrogen bonds to realign around the ions. Okay? So when you're looking at dissolution, if the overall process is endothermic, more energy was required to break the ionic bonds and hydrogen bonds than was released when those new dipole bonds were formed. So these new bonds just didn't have as much energy as breaking an ionic bond. Now, this statement right here, the dissolution of most ionic compounds is endothermic because ionic bonds are very strong. So you want to know the whole process from this diagram, but this statement's an important one. All right? If the overall process is exothermic, more energy was released when ion dipole attractions were established than was required to break the ionic bonds. Okay? So there are solids that we dissolve that actually get quite warm. When you take sodium hydroxide, for instance, and I make a solution, I have to be careful not to touch the beaker. That's how much energy is coming off. So a lot of it is kind of, the nature of the beast. You get those hydroxide ions, sort of, adding to the new bonds being formed, and the very strong new bonds. So it could be exothermic. Usually endothermic. The thing you would think of there is the little plastic packs that you have that you just punch them and break them, and then they are used for ice packs. That's an endothermic reaction, and what happens is you just basically are dissolving a salt in water, and it is an endothermic reaction, and it takes energy from the environment. So in terms of looking at the entropy, of course, a solid, super organized, very unnatural to be organized, as we talk about. This is much more natural to break up and get broken up. So that's the thing about entropy. If you have a really large change in entropy, then that can overcome the fact that these things, usually tend to be exothermic. So a lot of times they go from being very ordered to very disordered, and then that can be a driving force. So entropy is super important in looking at systems. So when an ionic compound dissolves in water, the entropy usually is increased a lot. The crystal lattice breaks apart and the ions experience a huge increase in their freedom, allowing for a large number of possible arrangements with those new ions. So just right down here at the bottom, right, just plus S, positive entropy, plus S. S right down there on the bottom, because that's the key idea. All right, now delta S can be negative in rare instances, and this would be one of those things that it's a good thinker type of question. So what that would be is if you had a very small ion, so top row kind of stuff, toward the upper right-hand corner where those small ions are, and aluminum having given up 3 electrons, it's going to make it even smaller. So this Al plus 3 ion is super small with a large charge, meaning 3, as opposed to a charge of 1 or 2 would be kind of borderline. So these ions can attract many water molecules because they're tiny, they got a really strong charge, and a lot of water molecules can fit in and around them, thereby reducing the entropy of the water. Okay? And that can be reduced to the point where the entropy of the overall system becomes less than of the components before they were mixed. Okay? So the key to this one is just knowing this exception. So highlight that first statement. Very small ions with large charges. Delta S can be negative, but that is definitely the exception. Dissolution is all about becoming more random and more disordered. Okay? So, if we look at this reaction, this might make you think of like KSP, where we talked about a solid dissolving into its constituent ions. So, if it's soluble, delta G is negative, and that means it's a thermodynamically favored process, and the equilibrium lies to the right. Both of those factors are true. For ionic compounds that are not soluble, they are not soluble because delta G is greater than 0, and the equilibrium will lie to the left. So this scenario right here wants to be mostly A plus and B minus, because depending on how big the delta G value is as well. Okay? So whereas this scenario right here that just wants to stay a solid, maybe a few ions, and we saw when we were talking about solubility that you can have just parts per billion of ions in just a very, very small degree of solubility, but we still call it insoluble because the equilibrium lies so far to the left there. Okay? So this is a really good summary of everything we've done actually over the past 3 lectures. So it's Friday, so this is kind of your own personal quiz. All right? So I want you to hit the pause, and what we're going to do on this slide for full credit is you're going to put your answers to these in pencil, and then we're going to go back and switch to some different colored marker or pen. So you might have to, grab a second different colored pen and correct it once we do that. So read that carefully. Of all the processes that are going on, I want you to be able to predict all of the big three that we've just learned about: delta H, delta S, and delta G. Okay? And I'll give you one hint. Do it in this order. Go delta H, and then delta G, and then delta S, and then do it in the order that they have there. I think that will work best. Yep. Okay, so hit the pause and predict the signs of each one of those and justify why it is that sign. Pause. See you in 1 second or 5 minutes your time. Hey, welcome back. So you need to have guesses for all 3 of those in pencil. And now in pen, we're going to either put a little smiley face or we're going to correct each one of these. So The first one, delta H. Well, the temperature of the solution decreases. That means it feels cold to the touch, and that's an endothermic process. So therefore, delta H, positive. Heat was pulled from the surroundings, and you know that because of the decrease in temperature, and that's what endothermic is. Okay? So, the next one is, you know that actually delta G is the next best one to do. So I was right there. I should have thought that through. So you know delta G is negative, and the reason that you know delta G is negative is it must be a thermodynamically favored process, or a TFP, as the equilibrium lies to the right, because it dissolved. An unknown ionic compound dissolves, right away you know delta G is negative. It's thermodynamically favored. And the hardest one was delta S, because it doesn't really say anything about the nature of the compounds. However, if you know delta G has to be negative and delta H is positive, you therefore know that delta S also must be positive, because this delta H is positive because it's endothermic, and we know that this overall number has to be negative. Therefore, this, if this was positive, then you'd be subtracting it, and that would not work out. So what you need is a positive number here, so that you're going to be subtracting the whole thing so that it ends up being negative. Because if you think about it, if this was negative and negative and negative, that's a positive, and then you would be even more positive, and it would not be, delta G would never get to be negative. So delta S definitely needs to be positive to produce that negative delta G. Okay? And so that was a good summary, a good test of everything that we've learned up to this point. And now we're going to start talking about electrochemistry and how that ties in, something that we did a lot of in general chemistry, and we'll get to that next week. Okay, so moving along real nice here. You're done with this lecture, and you need to put a little smiley face on this page to prove to me that you finished. Right up there, right there, a nice little smiley face going, hey, it's Friday and I don't have any AP homework, except if I want to work on the posted practice free response questions, and just to see how you can do on them if you want to start focusing on preparation for your future. Okay? All right. Sounds good. Have a great weekend, everybody, and take care.